So back for the main talk is Vesna Stojanoska, who will tell us about a particularly neat invertible K2 local spectrum at p=2.
Thank you, JD. And thank you all. I don't know. It's still early, so I'm not sure if I actually thought about how am I starting. Anyway, so I guess the end of last year, Agnes, Irina, Paul, and Hans Werner, and Viet Cong and I finally posted this paper in which we compute the exotic Picard group of the K2 local stable homotopy category at the prime 2. And there's a bunch of different things that go into that. The great thing about writing a long and technical paper like that is that I can give lots of different talks about it for a while. So here's a variation on something that's in there. But before we get started with all of that, I should introduce the usual suspects in this KN local world. And given that this is the eCHT seminar, I won't say much about them, but if anybody is interested or needs a reminder right now, let me know and I can remind you. So the way this works is we fix some prime P and we are always P local or P complete. But further, we fix even a height n. So n is going to be at least 1 for the things to work out. And it's a finite n for these things to work out the same way as I'm going to say right now. So that means we can talk about Kn local stuff. So Kn is some Morava K theory at height n. It can be built out of Lubin-Tate spectrum. So people, maybe we would write sometimes En or E of gamma n over K. So these Lubin-Tate spectra are spectra that are sort of attached to the deformation theory of some formal group law gamma n over a large enough field of characteristic P, which is perfect. But I'm not even going to say much about it, and I'll just write E for En and use all the naturality of this construction implicitly, as if I'm just picking one spectrum, but secretly there's a bunch of stuff going on behind the scenes. And then there's also the Morava stabilizer group. So Gn is going to be my name for the big one and Sn for the small one. And what is that Sn? So Sn is the automorphisms of this chosen formal group law over the field K. But how we do that, that's anyway, so which gamma n I will not mention, we choose is not particularly relevant right now, but again, as soon as we fix n to be 2, there is going to be a particular choice that goes secretly into a lot of math that feeds into what I'll talk about. And then the Galois group of the field with P to the n elements acts on this automorphism group, and then we have the stabilizer group. All right, so that is the usual suspects, and now I want to talk about Kn local Picard groups. I guess Hopkins back in the 90s introduced us or people who were there to this notion that so this is my notation for the Kn local category of spectra. The Kn local category of spectra is symmetric monoidal, with the tensor product being the Kn localized tensor product of spectra, or smash product of spectra. And the Picard group of this thing, just the group itself, is actually quite rich. So unlike just the category of spectra or the Picard group of the sphere spectrum, as we talked about in the pre-talk, so there was only the spheres. So Z, there was only a Z worth of invertible things. But in the Kn local world, there's much more stuff. And so this paper by Hopkins, Mahold, and Sadowski from 1994 is the first foray into this wild world of Kn local invertible things that appears to be sort of a gold mine for interesting mathematics. So one thing that they did in that paper is they gave us a recognition principle for when or how do we know if a Kn local spectrum is invertible. Okay, so the idea here is that we can test that by using our Morava E-theory spectrum. So this is or Lubin-Tate or Morava E-theory. So if we have a spectrum to know, or Kn local spectrum, to know that it is invertible, we just need to check that the E homology effects is equivalent to either the E homology of the sphere or a shift of it. So that means that this is in the Picard group of E star modules, because you may or may not know or remember that E star is a sort of so the homotopy groups of E are some complete local ring in pi 0. And then there's a periodicity class in degree 2 or -2, depending on how you set it up. Complete local rings in algebra, they don't have any invertible, non-trivial invertible modules over them. And then so we just have the shift of once, and then once we shift twice, we're back to where we started. So the recognition principle is that we just check it on E homology. But now whether the action of our group, of the stabilizer group on this thing is the same as the sphere or not, well, that's up in the air. So that's not something that can be predicted. So there's both kinds, right? But what we can do, and what Hopkins, Mahold, and Sadowski set up, is you take your X and you send it to this E star of X. Now, okay, that's an invertible E star module, but it also has this G action. And so what that makes it be, so it has this extra structure, and that structure is an invertible object in the category of what's called Morava modules. And what those are sort of E star G, or we could write that as a sort of modules over the twisted group ring E star G. So the homotopy groups of this Lubin-Tate spectrum have their own action of the stabilizer group, which is pretty complicated, but we can form a twisted group ring, and the Picard group of that twisted group ring in this graded way is cohomologically described is H1 of, I guess I left myself more spaces down here for this kind of stuff. But anyway, so we have that map, and this target of this map is kind of sometimes denoted by pic and alg. And even though most of the time we have no clue what that might be, there's this implication that it's algebraic, so not our business. It's just really hard to understand. So this is also a group of line bundles on Lubin-Tate space, sort of equivariant line bundles, and there's a whole yeah, so that's also a super hard thing. So anyway, that's also hard, but it's algebraic. And a lot of stuff in PICAN is generally seen here, but there's sometimes a kernel. Okay, so the kernel is called kappa n, and this is called by words is the exotic. So elements in here are called the exotic invertible object, or this is the exotic Picard group. So today I'll just focus on this exotic Picard group. But again, I just want to emphasize that there's so many fun and interesting and also completely intractable questions about this algebraic Picard. Okay, so any questions about this so far?
So if I went about trying to compute that algebraic Picard group, I'd be congratulating ourselves on the Galois group of FPN over FP. It's cyclic. I feel like I know group cohomology of a cyclic group down pat, even with this E star cross. We've got that algebraically. So I'd want to use a spectral sequence with the symmetric group and the cyclic group. And I guess
okay,
a priori, what did I do?
Kirsten, yeah, so I call this SN, but it's not the symmetric group. Okay.
Right.
Okay, so this is the automorphism group, and it's
I remember
it's some profinite group. It is a compact p-adic analytic group of dimension n square.
Is it QP star?
Yeah, for n equals 1 is ZP star. Yeah. So we have Sn is units there, and it's acting on Lubin-Tate theory at height 1. That is P complete complex K theorems acting by Adams operations.
So is it known there by algebra?
Yes.
Okay.
So that one. Okay, Siri is trying to solve my problems. Okay.
This is really helpful, Vesna. You don't have to stop.
Yeah, all right, that's fine. Sorry, I'm just like stop because I don't want to say anything and get this AI person jump out of my iPad, whose name shall not be said out loud. Right. So actually, the Galois group here is kind of the easy part because of Hilbert 90. There's some sort of Galois-ness in here, so you don't even have to compute cyclic group cohomology. You just take the Galois fixed points, and there's no higher cohomology. Okay. Yeah, so this group at n equals 1 is nice and very explicit, and we know everything about it. It's cohomological dimension 1 and so on, or at least virtually so. When n is larger, then that's when we have basically no idea. But so here's the examples that we do know about the exotic Picard group, although yeah, in some of these cases, something is known about this algebraic Picard group as well. So by some kind of usual comparisons, or what is now usual, so comparisons with Adams Novikov, vanishing lines and so on, gives that this exotic Picard group is trivial sometimes or often enough. So if P is large enough with respect to N, so this is the precise bound, and if P minus 1 does not divide N, so this makes the Adams-Novikov spectral sequence nice and sort of small enough, then that makes kappa N trivial. Now I'm wondering if I should say something. Let me say a word about it. Why? What does Adams-Novikov have to do with that? The point is that if X is in kappa N, what this is by the definition of kappa N, that means that the E homology of X is equivalent to the E homology of the sphere equivariantly. So that means that the Adams-Novikov spectral sequence for the homotopy groups of X, it goes like that. So we have the continuous group cohomology of the E homology of X, and it's going to be computing by T minus S of X. So the E2 page is then isomorphic to the E2 page for the sphere. Okay. And this isomorphism, algebraic isomorphism on the E2 pages, gives you a fundamental class, let's say a generator, iota X in pi z, so that determines this isomorphism. The question then of whether this X is the trivial object there, so it's S naught, or is something else, has to do with differentials on this fundamental class. And the situation here where if 2p minus 2 is greater than n squared, and if p minus 1 does not divide n, then that puts us in this kind of neat position of where the sparsity of the Adams-Novikov spectral sequence plus the vanishing line on E2 page. So this condition here ensures a vanishing line on the E2 page. So that ensures that there's no possibility for this fundamental class to support any non-trivial differentials. And so that makes the algebraic equivalence or isomorphism into a homotopical equivalence. So yeah, so that's kind of the moral of that is that kappa n is somehow interesting when the homotopy situation is complicated, when the prime is small. When n is 1, everything is known. And again, like the algebraic Picard group is known. The map to the algebraic Picard group is surjective, but I'm not going to say more about that. And then this condition here is satisfied when p is at least 3. So there's nothing there. And so the only non-trivial kappa 1 is the z mod 2 at the prime 2. And all of these things are done in this paper from the 90s by Hopkins, Mahold, and Sadowski. So that's right. Okay. So here's how the situation grows from here.
One more time, why you have an iota X? Like, I don't understand why determining the isomorphism.
Oh, right. So I guess here the X is just an invertible object. So it's not like it's just this module over the K local sphere in some sense. And so we have this isomorphism here It's an algebraic isomorphism. So iota x is somehow, so there's a 1 here, and that 1 corresponds to iota x in here, which is a G invariant. So it's something in H0 of G E0 of x, because 1 here, so 1 is invariant, and so it has to be sent to an invariant thing, and 1 here generates, so it's going to generate there, and this is going to give us an isomorphism on cohomology as well. In fact, sort of giving this isomorphism is equivalent to giving a suitable fundamental class in iota x with properties of this sort.
So it's not in all HS, it's just in HS for S equals.
Yeah, it's just in H0, and then so iota x is in H0, and it generates H star of that as a module over free of rank 1 over the cohomology of the sphere. It's not. So it's just a class in H0, but then everything gets propagated by it if we knew how things go for the sphere. Okay. All right, so what else is known? So here's at height 2. Okay, well, again, this kind of conditions apply, I guess, when P is 5. So there's nothing in kappa 2 in that for primes 5 or larger. When P is 3, there's actually 2 copies of Z mod 3. So this is already sort of like more interesting. We have something of rank 2. So this was done by Gorse, Mahold, and Resk, I think in a paper from 2015. So it was what, like 20 years? It took 20 years from from here to there's like 20 years. And it took a developing of this sort of resolutionary techniques in the K2 local, of the resolutions of the K2 local sphere and things along those lines. Okay. Now the P equals 2 situation, that's like as the newest development, and I guess we'll see when will this get published, if at all. So at least 8 years and many, many more pages, because as we decrease the prime, the complications keep growing. And you see the rank of this group is even larger. So there's 2 Z mod 8s now. It's not all like simple P torsion. So there's more fun going on in there. Okay, so for today, we'll just focus on one of these Z mod 2s in kappa 2. And the reason why this list ends is because that's all we know. So higher heights, who knows? There's some work by various people where certain elements are found of a certain order, so we know non-triviality statements, but the complete calculation is not known. So yeah, so now we're gonna switch to P equals 2. And from, I guess this is this pink box here is supposed to be telling you to P complete everything. So we're looking at K and local situation at the prime 2. And we'll look at this construction first that actually applies and at any height at the prime 2. But okay, any more questions at this point, or comments or concerns? This thing that I called the construction is the section title. So I'm going to try to show you a construction for a generator of this ZMod2 inside of kappa 2. But in order to construct it, first we're going to need to talk about certain maps associated to our stabilizer group Gn. So there's this determinant map that comes from the fact that, okay, so it is trivial on the Galois part. So where does the determinant come from is that this Sn embeds inside of matrices over sort of an extension of the p-adics by joining p to the n minus first roots of unity. And these matrices have certain type of symmetries such that the determinant map to here, that would be to this unramified extension of the p-adics. Well, actually, factors, okay, so that would be units in there. So there's some sort of Galois symmetry in the image that makes the determinants on elements in Sn land in the units in the p-adics. So at the prime 2, the p-adics are extra fun in that the roots of unity have two torsion or are exactly ZMod 2. So basically that's the cause of all extra complications at the prime 2 in homotopy theory. So we have the splitting of the two-adic units as the sort of plus and minus 1, and then the units congruent to 1 mod 4. So there's, you know, this group split, so we can look at the two projections. One is to this mu2 or C2, sometimes I'll write that, and the other one is the projection, the second factor, which, okay, multiplicatively, it's the units congruent to 1 mod 4, but there's a two-adic logarithm and exponential map that make that isomorphic to the additive group of the two-adic integers. And this bottom map here is called the reduced determinant, I believe. And there's a special name for the kernel of that map. It's called Gn upper 1. Okay. And this top homomorphism here is denoted by chi. And one thing to point out here is that, okay, this is just a homomorphism to ZMod 2. So therefore, chi also can be thought of as an element of H1 of Gn with coefficients in ZMod 2. Now I'm writing that as the, sorry, there's so many notations for this thing, depending on how you think of it. And now ZMod 2, well, that is plus minus 1, so we can include that inside of E0, and the units in E0, like E0 meaning pi 0 of E. Well, sorry, we can't include mod 2. That's right. So that's what I want to do. So then I can map this to H1 of Gn with coefficients in E0 mod 2 units. No, do I want the units? No, I don't want to put in units here. I just want to put that inside of E0 mod 2. Sorry, there's all of these things you could do, but I just want the plus minus 1 additively inside the mod 2 E0. Okay, so that is then some cohomology class that will show up in a little bit. Okay.
Could I ask you
yeah.
about the determinant? Is that that's not the same as what's called the reduced norm? You said it was trivial, but you said it was trivial on the Galois part, whereas the reduced norm of the Frobenius is minus p, or minus 1 to the n minus 1 times p.
Okay, so then I shouldn't be saying that word. Okay, all right. I think ultimately in terms of what these cohomology classes are, it doesn't matter. They're equivalent in cohomology. And in any case, we keep restricting to the small stabilizer group and take Galois invariance at the end, and nothing really matters. So maybe it's not even relevant for much of what, but thanks for pointing out that. I don't know. Is that an established terminology that the reduced norm takes the?
Well, in Morava's 1985 paper, there's a pretty standard, if that's a reference.
Okay, all right, thank you.
Yeah.
Great. So at n equals 2, another group that maybe is relevant for today's discussion is the maximal finite subgroup of Gn. And it's called G48 because it has order 48, that's its size, and that is in contradiction with this being G2, but so G2 does not have size 2 by any stretch of the imagination. But anyway, so there's this maximal finite subgroup, and all that matters for today is that this is inside the kernel of the determinant map of even of this first determinant up here. Okay. So all right, so now we need to use this thing to construct something. So we're going to construct a representation sphere, and with it in an invertible K and local spectrum. So how are we going to do that is the following. So we're going to use this map chi to construct an invertible object. So if I have a V representation of the cyclic group of order 2, here's something I could do. I could take the one-point compactification of V, and then smash with the Lubin-Tate spectrum E, and now I can act on G by G on this thing diagonally, where I'm acting on the factor E by the standard action, and on SV act via chi. So through this quotient chi, okay? So that is going to define an invertible object in the K and local category. So this is the sort of a very specific example of building equivariance into the construction from the pre-talk. So okay, so what will happen is that if we have something in the augmentation ideal, so that's now generated by this sigma minus 1, well, what that will do, it will make sure that if we forget this action, we shift by an even sphere. So if V is in here, it's going to land in what's called pick n0, and these are those X invertible objects such that the E homology is even. So there's no odd shifts there. But if we shift by so if we preserve the fact that we're in dimension 0, and if we shift by sort of twist by at least like 2 copies of sigma, then also the G action here on E homology becomes the same as the one on the sphere, because somehow twisting twice by sigma does not do anything on homotopy groups. So actually, right, so this part here, I mean, this construction, you know, we can make it at any point. So so here's a definition of a specific element in this Picard group, or in kappa n, if you want, and that is the image of the generators of the square of the augmentation ideal. So and let's call that Qn. So this Qn is there, and when n equals 1, it turns out that is one way to describe the generator of kappa, kappa 1 at the pram 2. What to say? I guess I was not I was imagining that the pre-talk will have covered the homotopy groups of this thing and all that, but we didn't get there. That's fine. I'll just state that. So if anyone wants to know more about it, let me know. I can talk more about it. So so at n equals 1, one thing that's different is that this z mod 2 or mu 2 is both so G1, yeah, so that is both a quotient and a subgroup. So G1 here is Z2 cross, which is this mu 2 times. So the determinant map is an iso 2. And so we get to choose if we wanted to compute, say, the homotopy groups of this Q1, we can do it by the standard sort of Adams, Baird, Ravenel approach. So we can compute that. We get that Q1 is, say, E smash this as 2 sigma minus 2 H mu 2 times Z2, and then depending on how we the order of taking homotopy fixed points, we get to understand this in a very, very hands-on, explicit way. Okay, so the theorem that we proved, among other things in this paper, is that at the height 2, so Q2 is a non-trivial element of kappa 2, and actually has order 2. So this is kind of both the same sort of situation as at n equals 1, but at n equals 1, all kinds of constructions you could do at height 2 become the same sort of thing. Example. There's this sort of bifurcation happening as you jump from height 1 to height 2. So a natural question then you might ask is this is something of, some part of the statement at least true for higher heights? And we don't know whether that's the case or not. Our method is rather computational, so you know, if such a thing is true always, there should be a better proof than what I'll try to sketch next. JD, I forgot, how long is this supposed to go on for?
45 minutes, so you have a little over 5 minutes left.
Great, thank you. Okay, so here's the sketch of the proof, or at least of the part that Q2 is a non-trivial element. Proving that it has order 2 is similar but more complicated. So, you know, for any of these, you know, Q was something, you know, the J homomorphism applied to 2 sigma minus 2. We could do that for any V in I2 and do a similar kind of calculation. So what we'd like to do is study this homotopy fixed point spectral sequence, which is actually the same as the K and local atoms Novikov spectral sequence that I talked about earlier. And then there's this fundamental class that I guess here I've called IV. And the question is, are there differentials on non-zero differential on this fundamental class? If there is, then we know we have a non-trivial element. So, right, so I guess I wrote that out as a recognition, sort of guidance principle. And what we end up showing is that actually there's a D3 that's non-trivial for this Q guy, and that D3 has a specific name. It is eta times chi tilde times this fundamental class. Okay, so eta is the same eta, the Hopf map eta that we all know and love, and chi tilde is the Bockstein on the chi we talked about. So chi was in H1 with coefficients in E0 mod 2. So the Bockstein then takes us to H2 of E0, which is something that that lives in there. Okay, so all right, so how are we going to compute this differential? Well, we start by trying to compare with something that maybe we can understand, and that thing is the homotopy fixed point spectral sequence for just the C2 action on this representation sphere. Okay, so this is fun because we know a bunch about what these homotopy fixed points are. So they're these kind of duals of stunted projective spaces, and so that's this means Spaney-Whitehead dual of the Thom space of the virtual vector bundle that's certain number times the tautological bundle on RP infinity. So we know a bunch about these things. Back in the 80s, they were heavily studied, but there's a lot of differentials in that spectral sequence here, not coming from that. So what we end up doing is actually, okay, we want to prove something about D3 here. So what we can do is we can truncate the spectral sequence and just look at the sort of truncated. So TOT3 is the thing that does it. And what that means is here S ends up being less than or equal to 3. So we just chop off everything above filtration 3 and above. Above filtration 3, we keep filtration 3. And here's a picture of what that looks like for the sphere, or for this representation sphere. And if you know what this diagram means, that's the cell structure of this truncated or stunted projective space, suitably shifted. And what that tells us is, it tells us that here, if we take this like this is, let's say the generator there, we could call it J. So that thing is going to support these D2 differentials. And here's, okay, so this is going to be a really speeded up version, but that's what we can do with the amount of time we have. So there's so there are those D2 differentials, and over here there's a class G, well, times this generator J, and G is a generator in H2 of C2 with coefficients in Z, which is pi 0 of the sphere. And maybe we need to complete it to two, but whatever, it's still the same kind of thing. But so what that means is that this G then gets sent to chi tilde that we saw up here somewhere. Sorry, I'm wherever that this chi tilde. So if we think about what this means, is that okay, well, our class GJ is a permanent cycle because nothing can hit it. And it's also the kind of thing, well, eta multiplication in this picture, eta is this way. So this is eta multiplication. But even if it jumped filtration, there's nothing there. So eta times this class has to be 0. Okay. But the class, that specific class, is non-zero in these homotopy groups. Now we study what happens in a map of spectral sequences. It gets sent to chi tilde times something rather, times our, whatever our name for the fundamental classes. And for the same kind of degree reasons, this class is non-zero. But the cool thing is that that class is detected by eta. So eta times GJ goes to something that's detected by eta chi tilde times the fundamental class in H3. And it has to be 0 because 0 can only map to 0. But it doesn't support any different. This is a non-zero class in the cohomology. That's another calculation. And so it has to be hit by a differential. So the only possibility is the differential that I've claimed. And so that tells us that we have this differential, and therefore Q cannot be equivalent to the sphere. So that's the brief sketch. And here I have just stated that the proof that 2 times Q2 is similar, but we need to take higher filtrations and higher truncations, and everything gets more hairy, and much more of the cohomology of the stabilizer group plays a role in that. So I'll end there. Thank you.
All right, let's thank Vesna again.